We spoke about Archimedes in our last video. This time we are going to pay tribute to this guy. I made a drawing of him myself here. His name, Robert Hooke. And let's take a look at one of his contributions in physics. Okay? Alright. Imagine we have two identical springs here. These springs can be stretched or compressed, which brings us to naming forces again. This one and with this one, which extends the spring out, pulling forces are called tensile forces. When we do the opposite, say pushing this end here while having another force here exerted by the object on the spring, like that, tend to shorten or compress the spring are called compressive forces. Let's see the dimensions and some quantities that we are to deal with in this topic. This spring, imagine we have one of these identical springs here. This dimension is its original length L when there is no force acting on it. Its relaxed form. When there is already a force, imagine this part of the spring pulled by a force like that. It will be extended here. And this distance between these 2 points, we are calling it x or extension or elongation. This is the effect of applying a tensile force here. Alright? Now, if we are to investigate the effect of force to the spring, and as most books are presenting, we can have a graph here with manipulated variable, the tensile force in newtons, and our responding variable extension x in centimeters. Expect that a graph that looks like this, rising straight line here at first, then somehow goes this way after a certain value of force applied on the spring. Sometimes people like to do the experiment differently by looking at this force. Restoring force exerted by the spring itself to the object that exert the tensile force here. Imagine you are pulling the spring, your force is the tensile force, and the force that you feel that is directed opposite to yours, trying to return the spring back to its original size and form, is the restoring force. Okay? If this is the case, your graph should look like this, with the restoring force here and extension here. The axes are interchanged, as you can see, because the extension is the one you manipulated this time and therefore along x, and that this extension affects how much restoring force the spring does. If you are using the same spring as in the first figure we have here, your graph goes just the same, like this as in the other figure, but goes this way after reaching a certain value again. Both of these graphs show direct proportionality relationship, which ends after this certain point. This point, guys, is called limit of proportionality. Alright, hold on, let's place this first here. Okay, so this point and this point, limit of proportionality. The direct proportionality relationship from the graph only applies before this point. Beyond the point, the relationship between force and extension is going to be different. Alright? As long as we do not reach this limit, extension x is directly proportional to the tensile force from this graph. Alright? And the magnitude of the restoring force is directly proportional to the extension x from this graph. Alright? This other graph here. Now, the proportionality constant is called spring constant. Varies from one spring to another, alright? But equal to the force over extension anyway. If we rearrange, this equation gives us force equals kx. And if you are looking for the force in this graph, the restoring force, you can place a negative sign here to mean that the direction of the restoring force is opposite to that direction the spring has extended. Alright? If you are interested on the magnitude of the force only, then you can just ignore that, alright? That negative sign. So here, we look at the deformation of a spring. In my discussion, I did not consider the thickness of the wire that made up the spring. We just look into a point where a force is exerted and the displacement of that point as a result. If you are trying to understand the same concept as applied to materials in general, you can imagine that this idea, F is equal to kx, applies to each particle in an object. Like when you pull particles apart, other particles tend to pull them back, exerting a restoring force. Let me give you an example as an extension of this concept to materials around us in a more general sense. Alright? Imagine this, a ceiling perhaps, and we have here a uniform material fixed to that. We can imagine that particles in this material are each behaving as if they are springs. We have lots of particles here, so we should have lots of spring. What I am trying to say is that there is a need to modify the F is equal to kx idea we derived from the graphs. There will be many particles here, or we can model them as many springs. Here, 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 and so on. Okay? Like that. The force, a tensile force, will exert acts on this whole area perpendicularly. That force will be divided among the spring models for particles here, and that the distribution will change depending on the area, isn't it? Larger area, more springs, and the force will be divided among them. With this idea, therefore, guys, we cannot just say that the cause of deformation is F, but the F per unit area. And if we do that here, there will be an extension here, extension X, but this X is dependent on the original length L. Again, if your original length or initial length is longer or shorter, the extension is affected. For a certain amount of force applied perpendicularly on an area, extension may vary depending on the initial length. In your mind, you can picture that a shorter length yields lesser extension and a longer one yields longer extension with that same amount of F over A applied on the material. The deformation of this material, therefore, should not be based on X, but on X, the extension or the change in length, over the original length. We can say now that this quantity F over A is the cause of deformation in a material, as the F caused the deformation in a hypothetical spring. On the other hand, the measure of deformation should be this X over L in a material, just as extension X for an ideal spring. People call this F over A here as the stress, and this extension over the original length here as the strain. And if we are to graph these quantities, we'll be having similar graph as when we did it to get this equation. The relationship between stress and strain is similar to the springs F and X. Stress is directly proportional to the strain. Alright? The stress experienced by the particles or the material as a whole is given by this F over A, stress, is represented by the lowercase sigma, this. Alright? For the strain, this quantity here, we use epsilon, this symbol. And since they are directly proportional, we can write that sigma over epsilon is equal to a constant. In physics, this constant, let's erase this first. This constant is usually given the symbol Y, perhaps because we are calling this Young modulus of elasticity. In some cases, in other schools or other books or other curricula, they use capital letter E for Young modulus of elasticity. In the case of Cambridge's exams, they often use E. So we are using that also for this constant. Alright? Alright, so this equation, guys, and this one too, applicable within elastic limits only, are the ones associated with the guy I mentioned at the beginning of this video, Robert Hooke. And these two equations are representation of the physics idea known as Hooke's law. Restoring force is directly proportional to extension in springs, and stress is directly proportional to strain in materials. Alright? Bye.